The solvent is a substance that dissolves a solute, so something that is chemically distinct, a liquid, a solid, or a gas, and what it results in is a solution. The solute is the minor component of the solution. That would be the liquid, the solid, or the gas that we're dissolving in the solvent.
There are a number of different concentration units. We are going to talk about one of the many, and one of the many is called molarity. Molarity is one way to express concentration, and it is given in terms of a volume, how much stuff there is in a certain volume. Other things give it in stuff of how much there is per amount of mass, for example. Molarity is defined as the moles of solute dissolved in the liters of solution. And you've got to be careful here. We're talking about solution, not how much solvent is in there. The unit on this would then be moles per liter, or we write it as a big M, which represents molarity. And we can then also say this as some molar value, molar concentration. So let's take a look. Let's start with a simple example here, and then we're going to build our way up. What is the molarity when 0.593 moles of HI, hydroiodic acid, is dissolved in water to make 0.25 liters of solution? We would take the molarity is the moles per liter of solution, and so we would take the 0.593 moles of HI and divide it by the 0.250 liters. And so we would get, if we calculate that, a concentration of 2.37 big M, which we would say is 2.37 molar. You could also write it as 2.37 moles per liter. That would also be an acceptable unit. This next example is actually worded more properly. It says, what is the molarity of a solution when 2.5 grams of iron 3 nitrate is dissolved in water to make 500 milliliters of solution? And so now that would be the real, more correct representation of how to do this. What we would do is, again, molarity is equal to moles per liter of solution. We actually know the liters of solution already. We know milliliters. So if I converted that to liters, that would be 0.50 liters. The 2.5 grams of iron 3 nitrate, that I would need to use a molar mass. I calculated the molar mass to save a little bit of time and found that 1 mole of iron 3 nitrate, is 241.86 grams or so. If you get a slightly different number, don't worry, the sig figs will essentially work that out in the end. And so when I calculate that, I get 0.010337 moles. I just wrote down enough numbers. We calculated that it was 0.5 liters of solution. And so when we divide that out, we get 0.0207. You might get 0.0206. That's also fine. That would be moles per liter, or capital M for molarity. So in the previous problem, we calculated the volume if we knew the molarity and we knew the moles. But we often don't know moles. We know how many grams there are. So in this case, it tells us there's 24.2 grams of cobalt 2 sulfate. Cobalt 2 sulfate. And I want to know how many milliliters of a 0.5 molar cobalt sulfate solution contains 24.2 grams of cobalt sulfate. So let's say I wanted to know, well, how many grams, if I need that many grams of cobalt sulfate, how many milliliters of a certain molarity solution would I need to grab in order to ensure that there's that many grams in there? And again, do we start with the molarity? No, we start with this. So I'm going to do 24.2 grams of cobalt 2 sulfate. The reason that it's a cobalt 2 is because sulfate's a -2 charge. Cobalt must be a +2 to balance that out. Sort of a side note there, but just keep that in mind. To get to, this is, if we think about this, 0.5 molar is the same as saying 0.5 moles for every 1 liter. I'm also going to give you a hint that in some cases we could write this as 0.5 moles for every 1,000 milliliters. The reason that that might be helpful is since we're asking for milliliters there. And so what we could then do is we could then say, well, let's find moles because we want to know milliliters. We have something that would allow us to find milliliters, but we need to know moles. So I'm going to do 1 mole of cobalt 2 sulfate. I found out that 1 mole of cobalt 2 sulfate is 155 grams per mole for the molar mass. And so that would cancel out grams. Now I have moles, and so I'm going to take this and I'm going to use it down there. But since I want to know volume, how many milliliters, I'm going to put 1,000 milliliters on top. I'm going to put 0.5 moles of cobalt sulfate on the bottom. And that's going to cancel out moles, and I'll be left with milliliters. If I do that calculation, I get a volume of 0.31, or well, in this case, the way I did it, I should automatically get 310 milliliters of solution as my answer there. We could also find out how many grams of something we need to dissolve, because obviously we don't have something that easily is used to find how many moles we have. At least, you know, if it's solid, you can't just go and put it on a balance and say, yay, there's that many moles. So it says how many grams of sodium bromide would be required to make 1.3 liters of a 0.40 molar sodium bromide solution. And as a reminder, don't start with the molarity when doing the calculation. So let's start with the 1.3 liters. Now, the idea is we want to find out how many grams of sodium bromide we need. So in order to do that, I probably need to find moles. So 1 mole of, well, in this case, I'm not going to do 1 mole. That's a good point to me. Let's come up here. If I go and get a bottle of 0.4 molar solution, it'd be 0.4 moles per 1 liter. So instead, I'm going to write 0.4 moles for every 1 liter. The reason that we do that is in this case is that we have a bottle of solution, or we want to make a bottle of solution that has that many moles per liter. So that would cancel out the liters. And then I would go and I would find the the molar mass to find out how many grams would be in the sample. And this problem in the notes I showed it as 2 steps, so you'll now see it as 1 step instead of it. So the molar mass of sodium bromide is 102.89 grams for every 1 mole. And so that would cancel out moles. And when I do that, I would get 54 grams of sodium bromide would be necessary to make that solution. So let's say that I wanted to find out how many grams of, that's glucose, you don't need to know that one off the top of your head, are required to make 450 milliliters of a 0.9 molar. And in this case, I'm going to assume it's a few more sig figs out there just to keep a little bit of consistency there in this case. I wouldn't start with this molarity because that's really the same as saying is 0.9 moles for 1 liter or 1,000 milliliters. I'm going to use that because my volume is in milliliters right now. And I'm going to start and say 450 milliliters, and I'm going to use the 0.9 moles. In this case, I can leave the ratio alone and write down 1,000 milliliters there. That would cancel out milliliters. And then I would, in order to find out how many grams there are, I would need to know the molar mass. The molar mass of glucose is 180.18. And so that would cancel out moles per 1 mole. And so when I do that, I get something around 73.0 grams of glucose that you would need in order to make a 0.9 molar solution in 450 milliliters. In a dilution, what you are doing is you are taking a more concentrated solution and you are adding water or some other solvent in order to create a more dilute solution. The idea is that it's going from a higher concentration to a lower concentration. And the amount of solute does not change during the dilution. A good example of this is if you think of making orange juice. If you were to take that orange juice from concentrate, maybe frozen stuff, and let's say you let it melt so it's a liquid. The idea is that it's concentrated. You then add water to it. The concentration of the orange juice goes down. There's not as many orange juice particles per volume. And so it goes to a lower concentration. But the amount of orange juice that's in there in terms of, how much you added is going to be the same still. There is an equation that is used to calculate dilutions. The equation is C1V1 equals C2V2. And you may see it sometimes written as M1V1 equals M2V2. I used to write it that way, and then somebody said that not everybody realizes that you can use other concentration units there in its place. And so you should realize that you can use other concentration units there. So C represents the concentration, and it can have units of molarity, percent concentration, parts per million, parts per billion, parts per trillion. All of those would be concentration units. V represents volume, and that can really have any units that it wants. It could have milliliters, liters, gallons. C1 and V1 are the concentration and the volume before the dilution occurs, and C2 and V2 are the concentration and volume after the dilution occurs. It doesn't necessarily matter whether you set one side as C1 V1 and the other side is C2 V2 as long as you're pairing up the concentration and volume that go together on each side. Similarly, it doesn't matter necessarily what unit you plug in as long as the unit is an approved volume or concentration unit and that they're the same on the both sides. Here's another example of a dilution. 29 milliliters of a 1.8 molar hydroiodic acid solution is diluted to 150 milliliters with water. What is the new concentration of the hydroiodic acid? And so in this case, we're saying that amount is going to be our starting point. It's then diluted, so this must be your C1, V1, and then this must be related to our V2. So concentration 1 is 1.8 molar. It's 29 milliliters of solution. And it's going to be diluted down to a new concentration, which we'll call C2, and the volume that we want to go down to is 150 milliliters. If we take and get concentration by itself by dividing by 150 milliliters, we get that concentration 2 would be a 0.35 molar essentially. You do get something like 0.348, and then we would round that off to 0.35. Does that make sense? Yeah, we got a lower concentration than what we started with. So we should also take a look at how you actually make this, because one of the questions that is actually of really the most importance is if you were to go and do this somewhere, how would you actually do it? And so it says if you want to make 250 milliliters of a 0.5 molar KBr, potassium bromide solution, from a 3.25 molar potassium bromide solution, how much potassium bromide solution should you measure out? So let's answer that part first. We want to make this concentration in this case, and we are starting with the 3.25 molar. I'll write the big M there for the unit. This must be my concentration at the beginning, because then we're going to a lower concentration. So this must be my C2 and V2. So we're going to start by using the equation that we've used up until this point, C1V1 equals C2V2. It's a 3.25 molar solution. I want to know how much of that KBr solution I should measure out, so that's going to be my volume. I want to make a 0.5 molar solution, so that's my concentration, and it's 250 milliliters that I want to make, so that's going to be my volume too. I'll divide by 3.25 to get the volume by itself, and I will get a volume of 38.5 milliliters. The idea is that solution, at the more concentrated solution, we want to add water to that in order to make 250 milliliters. So how much water should we add? I guess I'm going to change the color on that even. What we do is we say, well, okay, I want 250 milliliters, but I already have 38.5 milliliters from the sample that I measured out, so I would just subtract the two. And what that would do is it would tell me that 211.5 milliliters of water need to be added. Why? Because those two added together would give me the 250 milliliters of solution I require.